Today we're looking at our second unit, sinusoidal functions, which is our graph of a sine, our sine ratio, that we just did in our unit 1 trigonometry. Okay, we will look a little bit at cosine, but not the graph of tangent. Okay, so day 1, we're just going to explore periodic motion and behavior. And you're just going to be able to describe key properties of periodic functions, the period, amplitude, cycle, and the axis of the curve given a graph. So we're just going to start with a general example to get ourselves back into knowing what a sinusoidal graph looks like. So we have a coach measures the velocity of air as the gymnast inhales and exhales after working out. We can draw a scatter plot and sketch a curve of best fit. Okay, so we're just going to read these points. Remember, this is your x and this is your y. So you're going to go over 1 on your x-axis up to 1.5. So over to 1.75. Put a point there. Then you're going to 1.5, go to 1.24. Go to 0. 2.5, negative 1.24, about there. Over again, 1.75. Back again, and you can keep repeating this pattern. As you do all of the dots. Okay, so you should see as the graph, you're going to draw the curve of best fit. You should see a wave-like graph. Oop, missed that a little bit, sorry. A wave-like graph forming, okay? This is what a sinusoidal graph will look like, okay? And we're going to get into some definitions on how we'll know it's sinusoidal and some information we're going to be able to tell from a graph, okay? So if we extended the graph in both directions by continuing the pattern, we would get this. So it would continue and continue on and on, okay? So what we're going to do is look at some definitions of a graph or some terms, okay? So our first one that we're going to look at is a cycle, which is the smallest complete repeating pattern of a graph. The length of one cycle is called the period. So you're going to be asked a lot about the period. Okay, so you're going to find the smallest completing repeating pattern. Okay, so it can't over repeat, like it has to be exactly one repetition. So to looking at our graph, it's probably easiest if we start up here. This would be one of our maximum values. We go all the way down to our minimum value, and then we're back up to our maximum. And then the pattern would repeat again in this cycle. Okay, so you have to figure out the actual time here. You can also move it, so you could move it over if you wanted. There could be another pattern. Okay, there's one complete cycle. Okay, one complete period. Okay. You can move it along. There is actually no correct way of telling a period as long as you are doing just one full repeating one. So here, if I wanted to, I could do one here. So we could start at 0. We could go all the way up to our max, all the way back down to our minimum, and back up to 0. And that would be one full period. Okay. And then the pattern repeats itself. So it goes up and goes down and then back again, up and then down and then back again. Okay, so that's what you're looking for. For our gymnast, the period is going to be from 0 to 4 seconds. Before we looked here, so we looked at the max to here, it would have been at 1 to 5 seconds, which is fine. 5 minus 1 is going to be 4. Okay. So you're just figuring out how long it is. It's going to be the value on your x-axis. Okay, remember that this can be drawn many different starting places, but always stops when you turn to the same place that you started. Okay, another definition we're going to look at. Also, you don't need to draw this graph again. So if you drew it here, don't draw it again. You can just start to mark on the same graph. Just write down your definitions and you'll draw those differently on your graphs, okay? So what we're looking at now is something called the axis of the curve. So the axis of the curve is the horizontal line. Remember, horizontal is this way, okay? Halfway between the minimum and the maximum value, which is called the axis of the curve. So here you could look at the maximum value, so 1.75. Negative 1.75 is your minimum. Well, what's exactly halfway between would be at 0. So you're going to mark y equals 0 there, okay? However, sometimes graphs aren't that nice or their numbers are a lot bigger. And if you want to make sure, you can use a formula for the axis of the curve. So your axis of your curve is going to be a y equals. You're going to do your max value plus your minimum value and divide it by 2. So our maximum value is 1.75 plus our minimum value, which is negative 1.75. Make sure you put that in brackets because we don't like the plus and negative beside each other, which is then 2. So then you're going to get 1.75 minus 1.75 divided by 2. So 0 divided by 2. So then y is going to be equal to 0. Okay, so your axis of your curve is going to be 0, and because it is a y, you have to put your units for y, so it would be liters per second. Okay, your amplitude, so another definition, just copy out this definition, is the distance from the center of the axis of the curve to the maximum or min. So you're looking here and on your graph, you're either looking at from your axis of your curve up to your max or your axis of your curve down to your minimum, okay? Again, this is quite easy to see. Well, 0 to 1.75 is 1.75. 0 to negative 1.75 is 1.75. But if your graph isn't nice and it's bigger numbers, you can't read it for whatever reason, you can use, or say you don't have a graph, you can use your amplitude. It's going to be max minus min divided by 2. So your max is 1.75 minus that negative 1.75, all divided by 2 is equal to 1.75 plus 1.75, all divided by 2, which is 3.5 divided by 2, which is 1.75. Okay, and that is going to be liters per second as well. Okay. Last one is extrapolation, is the process of extending the pattern to make predictions. So here we have our gymnast, and we're in the process of extending the pattern to make predictions. So we are going to find, for our gymnast, what will the velocity of air be after 60 seconds or after 38.5. So we need to extend this pattern. So we only have our graph up to about 13 seconds. We need to extend our graph to figure out what it's going to be after 60 seconds, 38. So you can just use some points in the pattern to help you. You don't actually have to draw it all the way over to 60 seconds. Okay, so let's look at 60 seconds first. And this one is quite easy if you can recognize the pattern of where 60 seconds is going to be an even number, correct? Okay, where are all the even numbers? 0, 2, 4, 6, 8, 10, 12. They all fall on the x-axis at y is equal to 0. So you know that 60 seconds, is going to have a velocity of air of 0 liters per second, right? Just like from extending that graph, knowing all the even numbers are on that, okay? Now, for 38.5, we can kind of use the same. So we know that the even numbers all fall on the x-axis at y equals 0. So 38 would be on the x-axis. And then we know that either it needs to go, it'd be like 2.5, right, went down to our negative 1.24, or 4.5 went up to our 1.24. So it's either going to be positive or negative 1.24. So if you were to continue 2, 4, 6, 8, 10, well, it's 38 is like having it on the 8. So you know that it's going to go over and then it's going to go up. So it's going to go over to positive 1.24. Okay. Okay, so just wrote exactly what I just described there. Sorry, this is is. Okay, sorry, that was my marker's not working that well. Okay, so what I need you to do here as well is, if it says explain, just explain your thinking of how you extrapolated on that, okay? Or extrapolated. People say that different, okay? So those are our like definitions we're going to look at, and now we're going to look at Ferris wheel and actually get into our sine graph, like specific sine graph, without using a gymnast, okay? So objects that travel in circles certainly display periodic motion, okay? Object will reach a maximum distance above the center of the circle, so there's your center. It will reach a maximum distance up here, and it will reach a minimum around there, okay? The distance, this distance, so here to here, would be your amplitude, or here to here would be your amplitude, okay? The period is the amount of time it takes for one complete rotation. So if we started here and we went all the way around our circle, that is going to be one period, okay? So it's the amount of time that it takes you to get around there, okay? These are really important. You'll see a lot of Ferris wheels when we get to solving problems with these, okay? Because they're a great example of a periodic sinusoidal function, okay? An example here, so just let me grab my mouse, is how we get our sine graph to actually be drawn. So just take a second to listen to this and watch this.
We have all seen pure tones illustrated as sine waves, but each moment in the sine wave's formation has a different phase associated with it, from 0 degrees to 359 degrees. You can see the sine wave forming here, and the round protractor on the left shows you the equivalent phase at particular moments in time.
Okay, so you can see it's being graphed at 0, 9.
If you use the various points on the rotation of the protractor and draw those points on the graph on the right, you can create a drawing of a sine wave.
Okay, so what we're going to actually get into now more specifically is drawing our sine graph. So if you have y equals sine theta, theta is, remember, is just degrees. Okay, so you're going to look at 0, 30, 45, 60. So if you were to put in your calculator just sine of 0, you should get 0, and it's going to graph down here at the same time. Okay, if you put in sine of 30, you should get 0.5. Sine of 45, 0.71. Sine of 60, 0.87. Sine of 90, 1. If you keep going and keep putting all these values of the degrees in your calculator, of theta in your calculator, you will get a graph of something that looks like this below, which is our sine graph, okay? However, it can continue going. We could go negative degrees, and we could continue going past 360 degrees, okay? Of course, but for speed and simplicity, we're going to focus on major points for our sketches. So, okay? So the ones that I want you to focus on are these ones. 1, 2, 3, 4, and 5. So the 5 points that you're going to sketch are going to be 0, 90, 180, 270, 360 if you were to just draw it like this. And then it is at 0, 1, 0, negative 1, 0. This is something that you're going to want to have memorized for like the next 3 lessons. We will use this at the beginning of every graph we do usually. Okay. On this graph, it's going to be look at 0, 0, 91, 180, 0, 270, negative 1, 360, 0. Okay. And then you would just connect the dots. You do not need to extend the graph even further for your base function, sinusoidal function graph. Okay. So just these 5 points to start. When we graph this, we can actually look. So we found our values in degrees. We also know values in radians. Don't worry about this too much. The only one thing that you might see is that one complete cycle or period for our sinusoidal function is 360 degrees, right? We start at the 0, we go our max, we go back, go down to our min, and then we're back at that 0. That's one complete like wave, if you want to call it that, okay? That in the radians is equal to 2 pi. You will see that a little bit. So just know that one cycle is either 2 pi radians or 360 degrees. Okay. Your exact values of sine x, these should look familiar. What are these from? That is from your special triangles. Okay. And then if you were to solve any of these, so either pi over 6 1/2, put it into a decimal, would be 0.5. Pi over 4, 1 over root 2 would be 0.71. So those are where your decimal values come, okay? That's specifically for sine of x. What you're going to want to use is that chart that I just showed you, the 0, 90, 180, 270, 360. That's what you're going to be using, okay? So when you're looking at our sine graph, there's some key things that you need to know that will never change for our base sinusoidal function graph, okay? Our period is 2 pi. Or 360 degrees, as I just talked about there. Our axis is y equals 0. So if you were to draw that, it's going to go right through our graph at y equals 0. Okay. Our amplitude, we go from 0 up to 1 or 0 down to negative 1. So our amplitude is 1. Our maximum value is going to be at 1. It will never get higher. Our minimum value is at negative 1. It will never get lower. Our domain, if anyone remembers domain is the value of your x's. So the value of your x's, because this graph continues on forever and ever, it's not in the context of a word problem. It's going to just continue on and go, go, go. So it has no restrictions. So remember when you're telling me your domain, your range, you're looking for restrictions. But since it has no restrictions, you can either say that it is theta as an element of the real number system, or you can do x as an element of the real number system. I'm fine with either of those. Okay, for our range, we have y as an element of the real number system. Remember, this means such that. And then you're looking at your restrictions. So y, our value of our y, so up and down on our graph, cannot go higher than positive 1 and cannot go lower than negative 1. It can only be the values in between that. So the way you read this is y is an element of the real number system such that y has to be greater than or equal to negative 1 or less than or equal to positive 1, okay? So just keep that in mind for your base sinusoidal graph, okay? We are going to look at our cosine graph as well, so cos of x. Same thing here, other than the points for 0, 90, 180, 270, 360 change a little bit. So I'll put it here. So cos x, so you're going to have x and y. You still have 0, 90, 180, 270, and 360. You still have those values, except for now at 0, you're up at 1. At 90, you're at 0. At 180, you're at -1. At 270, you're at 0. And then at 360, you're at +1. Okay, so it looks almost the same. It's just your starting point. Instead of starting at our origin, we start up at 1. And then you can graph those points there. Okay, and you would connect them. Okay, same thing. Our period for cosine is still 360 degrees or 2 pi. Axis of symmetry, or our equation of our axis, is still y equals 0. Amplitude is still 1. Max value is still 1. Minimum value is still 1. Our domain and range would still be the same as well. Okay, so the only difference is how you draw this graph. So this is key here, this chart that I just drew. Okay, so you may want to copy out that chart for our cos of x. Okay, we're just going to get into a couple of examples of how we are able to identify sinusoidal functions. Okay, so it just says which situations and then justify your decision. So the graph repeats over the same interval, so it doesn't even really have time, but it's going to repeat and repeat and repeat. Okay, so it's periodic, so you know that it's going to continue repeating. It keeps its maximum minimum value, and because it's the same shape as sine of x, and that's meaning it has this like wavy flow to it. Sorry, it's not totally accurate. Okay, you cannot have something that's like pointed or anything like that. You couldn't have like anything that's not wavy. Like you can have like something that repeating like that. It has to be your wave. Okay, so we know that it is periodic and it's going to be sinusoidal. Okay, for this one, the depth of a programmable radio-controlled toy submarine. So we are going to start, we have a little hump, the big hump, then little back, and then we're back to the beginning right here. So there's one cycle of our graph, okay? And then it repeats itself again. So it is actually going to be a periodic graph. However, it cannot be sinusoidal because it is not the smooth waves, okay? It cannot be like that. It has to be identical to this. It can't have all these little jolts and everything, okay? The motion of a flagpole is in a gust of wind. So again, does it repeat? So does it go from the same maximum here, same minimum, and back up to the same? Nope, it's going even higher, and then it goes even lower, and then it goes higher, and then it goes lower, higher. So it cannot be periodic because it's not repeating the same pattern, because your pattern is not the same by getting higher and higher or lower and lower, okay? Nor is it sinusoidal because it's not periodic, okay? It has a sinusoidal functional graph has to be periodic, right? These waves continue, and since it's not periodic, it can't be sinusoidal, okay? And then one more example, we're just going to interpret a graph. So we're going to look at a sinusoidal and periodic graph, which is Sarah's height above the pool bottom. And we're going to figure out what our period is, what our equation of axes is, and what our amplitude is, just so that you know how to do that from a word problem, okay? So Sarah's sitting in an inner tube in a wave pool. The depth of the water below her in terms of time can be represented by the graph shown. Discuss and interpret the graph, okay? So we're going to figure out what our period is. Remember, our period is the length of one cycle, so where we repeat. So you can tell from multiple different parts. So I'm going to start at 2. I'm going to go up to the maximum, down to the minimum, and then come back up right where we start at 2 to go back up to the max. So if you look at one cycle of your graph, it is going to be at 0, and then it goes over to 3. Your time is in seconds, so your period is going to be 3 seconds, okay? You could have told from over here. So say you want to start here at 2 seconds. Oh, and then you go down first, back up, go to the max, and then you're back over to 2 seconds. Well, between 4 and 7 seconds, the difference is 3 seconds, so you can tell that way as well, okay? It's up to you where you start, but you just need to make sure you complete one full pattern. Our equation of our axes. So remember that we're looking for that horizontal line that's halfway in between our max and our min. So if you're good at like looking and eyeballing, you know we go up to about 2.4 and down to about 1.6. So halfway in between there would be at 2. Okay, so it splits the graph evenly in half. Or remember that we can use our equation, max plus min divided by 2. So the maximum of your graph is 2.2 and the minimum of your graph is 1.6. Okay, and then you're going to divide it in 2. So it's going to be, that would be, if you want a middle step there, 4 divided by 2 and then equals 2. So you know that you have an equation of your axes at y equals 2. Okay. Then the last thing we're going to look at before you get started on your homework is just the amplitude. So here you had your equation of your axes at y is equal to 2. And you're just looking to get the max or the min. You're looking from that point up to your max or down to your minimum. Okay, so you're going from 2 to up to 2.4. So it's a difference of 0.4, or from 2 down to 1.6, which is the difference of 2.4, or sorry, of 0.4. Okay. Another way, so this isn't using the equation quite correctly. So that remember that your amplitude is going to be your max minus your min divided by 2. Your max is 2.4 minus that positive 1.6, all divided by 2. So 2.4 minus 1.6 is going to, or divided by 2, sorry, 0.8. Oh my gosh, I'm rushing, sorry. Divided by 2 is 0.4 meters. Okay, should add meters in there. Okay, so you're just able to determine and look at a equation a graph as well, and interpret it by finding amplitude period and your equation of your axes. Okay, so here's your homework. Use your notes at for 4BC. Okay, and then let me know if you have any questions. Good luck.